Let's inflict a little bit of calculus on our parametric equations. In the problem on the top, we're going to find the points on the parametric curve, which has parametric equations x equals t plus 1 over t, y equals t minus 1 over t. We're going to find the points on that curve that have the slope of the tangent line there equal to 1. In parametric equations, a quick trip through the chain rule tells us that the dy dx that we still need to figure out slopes of tangent lines, because we're still plotting these things in the xy frame, and so rise over run, if you want to call it that, is still the measure of our slopes. Chain rule tells us that dy over dx is dy over dt divided by dx over dt. And in this particular case, these are not tough derivatives. The derivative of y with respect to t will be 1 plus 1 over t squared, and the derivative of x will be 1 minus 1 over t squared, and then we'll multiply up and down by t squared just to tidy this up, and that'll give us t squared plus 1 over t squared minus 1. So that's the representation of the slope at any point on this curve, where if you plug in the value of t that you're interested in, you can get the slope of the tangent line back. We are looking for where that expression will give us a 1, and the answer is nowhere. So this was kind of a trick question. T equals 0 gives us 1 over negative 1, which is negative 1. It would not be possible for this expression to give us a 1. So let's say I tried to solve t squared plus 1 over t squared minus 1 equals 1. Cross multiply by that denominator and get t squared plus 1 equals t squared minus 1. The t squareds cancel, and that says 1 equals negative 1. Well, that's nonsense. And so that means there was no solution to that equation. All right, the rest of the lessons regarding calculus of parametric equations is that with parametric curves, we can measure area under a curve, we can measure the arc length of a curve. Pretty much anything we measured on curves written in rectangular coordinates, we can do the same with parametric equations. You just need to know the alternate form for the recipe. So in these cases, the construction of the integral is the important thing. Once you have that integral, you don't necessarily need to write out all the details of the by hand solution. Again, I will encourage you to develop your threshold, where when you see an integral and you have the option to do it by hand and you know you can do it quickly, go ahead and do it quickly. Don't rely on your tech as a crutch. Use tech when you need it. If it's going to take more time to go turn on the computer, type a bunch of stuff in and get an answer than it would have taken just to do the dang integral yourself anyway, then just do the dang integral yourself, right? This one will be one of those where we're going to get the integral, and then I'll just tell you that if you want to see the final value of it, you're free to go use some tech to get there. The expression for the area of a parametric curve, which you can find in the notes, is an integral, but it's a little more complicated than the normal integral for area of a rectangular function, but it's not too bad. We just need to plug this function in as it is, put on our limits for t. Now the functions were given in terms of theta, so I guess I should, just to be good, let's make these thetas right here. Doesn't matter what the parameter is, we still do the same thing. So the function with respect to y is 2 sine squared tangent theta. It looks scary, but it's actually going to help us out a little bit. And then we multiply by x prime, which from 2 sine squared theta, that derivative will be 4 times sine of theta to the first times cosine theta d theta. This is a gigantic mess, but remember that tangent is sine over cosine, so this cosine will cancel with the denominator of that tangent and leave behind a sine, and now it looks like we have, 4 of those sines altogether. There's also a coefficient of 8. So that's the the integral that needs to be resolved. If you want to throw some trigonometric integration at it, go for it. This would probably need a reduction formula you'd have to look up. So this is definitely one that just going and using some tech to get the final answer would definitely be fair game.